This problem gives us a circuit with a switch that can be in two different configurations. For the first part of this problem, the next one will be a separate video. We're throwing the switch to position A, which means that we have a circuit just like this, and we ignore that part in the circuit. Nothing's connected to it, no current flows through or anything like that. So the first question asks us to find the time constant tau. Well, that's just a matter of multiplying these two things together. So 800 times 10 to the 5th ohms times 5.00 times 10 to the negative 6th farads. Let's see, what does that equal? That is 4 seconds. So a simple little calculation. The next thing it says is to find the maximum charge on the capacitor. Well, that is also a simple calculation because we know capacitance is defined as the charge per unit voltage, per potential. So, and we can say this is Q equals C delta V, or we can also call this Q max. So this is equal to 5.00 microfarads times 12 volts. So Q max, that's kind of the way I prefer to write it, is equal to 60 microcoulombs. So the next thing it says is to find the maximum current in the circuit. Well, there are two ways we can approach this. As soon as the switch is thrown, there's no charge on these plates, so these plates offer no resistance whatsoever to the current flow. So at that instant when the switch is thrown, the current is going to equal the current as if that capacitor wasn't there at all, as if it was just a straight line connecting the resistor. So in that case, V equals IR, I max is just equal to V over R, or let's see, the voltage is, I'm sorry, this would be E. We're using E for EMF, electromotive force, which is essentially the same thing. That's 12.0 volts over the resistance, 8.00 times 10 to the 5th ohms. I max is 15.0 microamps. The other way we could do that is, I'm going to circle back to that in a moment, because the first thing we need to do is find the charge and current as functions of time. We'll see if I find the current as a function of time, I can go back and calculate I max, but let's put that aside for now. So the charge as a function of time is just Q of T equals Q max 1 minus e to the negative t over tau, or over RC. And we already have the time constant, and we already have Q max, so we can say Q of T is equal to 60 microcoulombs times 1 minus e to the negative t over 4.00 seconds. Now, how am I going to find the current? Well, remember the current, we use a lowercase I to denote this is a current that's changing with time. Current is equal to dq over dt. We're finding the derivative of charge, the change in charge per change in unit time. So that's equal to dt of this equation up here, 60 microcoulombs, 1 minus e to the negative t over 4.00 seconds. So the derivative of that is going to be 60 microcoulombs, that's a constant that just comes out, times the derivative of 1, which is 0, and the derivative of this, which is just plus 1 over 4.00 seconds, times e to the negative t over 4.00 seconds. So I as a function of t is equal to, multiply this out, that 60 is times 0 is 0, 60 microcoulombs over 4.00 seconds, e to the negative t over 4.00 seconds. All right. Let's see. 4 into 60 is 15. I of t equals 15.0 microamps. Carry the micro, e to the negative t over 4.00 seconds. So we have that. Now what is I max? Well, I equals I max at t equals 0. So I of t equals 0 equals 15.0 microamps times e to the 0th power, right? Which is just 1. So I max is 15 microamps, which is what we found up here. So everything works.